selection. But how would you do such a selection in practice?
For the real situation, I think this model can define that which cone that we can remove it by see the predicted value, that if the predicted value is 0 or minus value, we can assume that this is non-producing clone. That's why this model can determine. But when we look into the positive clone, we can quantitate how much of the antibody production.
Okay, thank you. In view of the time, I may have one short question.
That's okay.
Okay. In chapter 4, you use two compounds, adenosine and cordycepin, to increase the antibody titers. But I read in your chapter 4 that cordycepin is a derivative of adenosine. But what is the difference between those two compounds actually?
For the adenosine and cordycepin, there is a closely of chemical structure. As I know that adenosine is the nucleoside, that is the natural one and is involved with for the ATP synthesis. But for the cordycepin, because the structure have no the 3-hydroxy group, so maybe there is some different of mechanism of action in the DNA or RNA synthesis. So that might be have the different activity for the cell culture.
Yeah. Okay. Thank you. Thank you for your answers.
Thank you, Dr. Van Osten. Madam Doctoral Candidate, the board of the conferral of doctoral degrees of the Utrecht University now grants you the opportunity to defend your dissertation in public. And before we start the opposition, I would like to extend a special Please take your seats. special welcome to the second promoter, completely coming here from Thailand, Professor Yamabai from the School of Biotechnology of the Sunari University of Technology in Thailand. Very welcome here. I hope you enjoyed the ceremony and your stay in the Netherlands. Also, two other persons from outside the Utrecht University. Dr. Marieke Klein of the Department of Process Engineering of the University of Delft, and also of the University of Delft is Professor Dr. Michel Epping, also of the same department, Department of Bioprocess Engineering. I invite the first opponent, which is Professor Epping, just introduced to you, to start with the opposition.
Thank you, Mr. Rector. Dear candidates,
And the discussion will now continue by the second promoter, Dr. Yamabai. Yes. And please take the floor.
All right. First of all, congratulations. You have done so far, and I thank Utrecht University for educating you and the committee member for making this. I guess my question would be related to for Thailand. You know that we cannot produce therapeutic antibody yet, and it's very expensive drug. So do you think we should produce by our own in Thailand? And you have learned from this university, and you think if you think we should produce, what would be the next step? How can you help Thailand to make antibody?
How clear the opponent? Yes, it's quite difficult task for Thailand to make the own biologic drug, even for the biosimilar. But as I have knowledge now, yes, I can contribute for the upstream process, at least for the small scale and also the 5 liter of bioreactor. And then for the selection, high producing cone also. But anyway, for the manufacturing of the biological drug, it also have other steps, such as for the downstream processing and also the physical chemical property characterization. So I think if we would like Thailand to make the own biological drug, we need a team that composed of everyone involved with this step. So I hope that we can do in one day.
Right. I mean, you are the hope of the country. Okay. Right. I can continue.
Yes.
Yes. All right. Yes. Of course. Not only you. We will have. You are the one of the important human resource of our country. And maybe I go back to another question. Is that you have used a show DHFR system for the model of the study of all these chapters that you report. But then, what do you think you can translate this knowledge into another show system like show GS and other shows?
Yes, I think so. But because as my study, I have the result that compare the production between show DHFR and also show GS, and I found that there was a different response to the chemical additive between these show cell line. So anyway, I think if we would like to apply the good result or positive result from the show DHFR for the show GS, it need to validate the experiment, and also it need to optimize the experiment like presentation.
The committee will now withdraw for further deliberation. The session is adjourned. Please take your seats. I hereby reopen the session. Madam Doctoral Candidate, this committee, installed by the Board of the Conferral of Doctoral Degrees, has considered your dissertation and has heard your defense. The committee has decided to confer on you the title of Doctor. I now kindly ask the supervisor, Professor Mastro Battista, to invest you with the honors in the traditional fashion.
By virtue of the authority conferred on us by law, and according to the decision of the Board of the Conferral of Doctoral Degrees present at this session, I hereby confer upon you, Salantip Yarusuntanakorn, the doctoral degree to which are attached all rights and obligations towards science and society as laid down by law and custom. Do you promise always to perform your duties according to the principles of academic integrity, honestly and scrupulously, critically and transparently, and independently and impartially?
I promise.
Then I present to you with the diploma signed by the rector and supervisors and bearing the Great Seal of Utrecht University. Congratulations.
Thanks.
Are there any pictures? Yeah? Okay. Please, there's more, of course. During your stay at Utrecht University, you also followed quite some courses, for which we also have a training certificate. That is maybe a good remembrance of all the courses you have done, and something you can show to any person interested in what you have learned here. In addition to that, to remember your time in Utrecht, we also have this medal, the Uips medal as we call them, where you can basically see the entire chain of drug development, to which you have contributed a small bit. And I think it's a nice remembrance that you can take with you to Thailand. And that's not all. Of course, I think I can continue, right?
You can just
I also would like to say a few words now that the official part is over. Die laudatio. So, dear Dr. Yarusuntanakorn, dear Salantip, congratulations on the significant achievement. An achievement that could only be accomplished by perseverance and patience. I also extend my warm regards to your family, particularly your parents, who are undoubtedly watching this live stream with immense pride. Your doctoral journey began in 2014 under the supervision of Professor Huub Schellekens and Dr. Andy Khalib, supported by a Maidol University Academic Development Scholarship. Your initial project focused on the in-house development of alemtuzumab biosimilar, with the aim to make an affordable and thereby accessible alternative to the originator for patients in low and middle income countries. The first step was to design the plasmid construct for recombinant expression of this monoclonal antibody. To expedite the process, we opted to outsource plasmid production, a decision that, in retrospect, presented unforeseen challenges. Upon receiving the plasmid, you eagerly commenced transfecting the CHO cells and selecting high producer clones. However, despite numerous experiments and ELISA assays, no or low signals indicating alemtuzumab production was poor or absent. We initially blamed the sensitivity of the ELISA and spent quite some time in trying to optimize this, including the development of immunoliposome-based ELISA to increase the sensitivity. But to no avail. We started to doubt if the sequence we obtained from the company was actually right, and after sequencing the plasmid, we found out there were indeed mutations that explained all of this. After more than a year into the project, it was discovered that the plasmid contained mutations. I already said that, sorry. We were back to square one. Furthermore, the extensive pipetting required for the ELISAs led to repetitive strain injury in your wrist, temporarily halting your progress. We then transitioned into a new project involving automated lectin microarrays for rapid glycoprofiling of recombinant antibodies, and you made steady progress with that. Unfortunately, after quite some time in the Netherlands, your scholarship concluded, necessitating your return to Thailand. Despite substantial work and several initiated projects, completion of your thesis was still far away. Moreover, Professor Scherken's impending retirement added to the uncertainty. Frankly, at that time, I was quite concerned about the feasibility of getting your doctorate. However, you remained resolute. And as the Dutch saying goes, als de nood het hoogst is de redding nabij. Help arrived when Professor Yamapai from the Institute of Agricultural Technology at Suriname University of Technology provided her guidance and laboratory space. This allowed you to progress smoothly, leading to 3 research chapters and publications on optimizing antibody production in CHO cells by applying multivariate data analysis and by the addition of supplements in the growth medium. Soon, the prospect of getting your PhD at Utrecht University was realistic again. This would not have been possible with the help of Professor Yamapai. My sincere gratitude for all your efforts and for your willingness to guide Sanatip in a journey in Thailand. And I also would like to thank the members of the Reading Committee and the Promotion Committee today present, as well as all who contributed to this thesis. Special recognition to Andik Halim, Huub Scherkens, of course, and Maripas Marquez for their assistance with the EPO stability studies. Sanatip, you embarked on this long journey to Utrecht with a clear objective, getting your doctorate degree. You faced numerous challenges, but you persevered. Your perseverance and patience are commendable. While Professor Scherkens and I were not always prompt in our responses, but we have often slowed down your progress, your determination remained unwavering. Now you are a Doctor of Philosophy from Utrecht University, an accomplishment you should be very proud of. But that is just a piece of paper. The perseverance and patience that you have shown is a quality in life that can bring you further than any doctorate. And no matter how big the problems you face, you always kept smiling. But today, your smile is bigger than ever. Dear Sanatip, once again, congratulations with this big achievement, and I wish you all the best in your future career, and I hope we keep in touch. I've said.
Thank you for this summary of the history and this appraisal. Very learned, madam. On behalf of the board of the conferral of doctoral degrees, I congratulate you on the honors which have been bestowed on you. I see on your thesis some nice molecules referred to as monoclonal antibodies, and we know they are all well targeted. I hope that this certificate, PhD certificate, will target your further career in life. I hereby conclude this session.
say that I have read your thesis with pleasure. It's very nice to read because I'm quite well in this field of biopharmaceuticals, and there are very nice chapters, topics in this thesis. I have a first question that is in chapter 11 and of let's say chapter 1 in let's say page 11 and 12 you give an overview of examples of genetic manipulations to improve the productivity of CHO cells. My question is, do you have also an idea whether it improves, let's say, normally for CHO cells, you get a very high expressions levels? And secondly, have you any idea about the new technologies like the transposase technology?
How clear their opponent? For the first question, I think for the genetic engineering, maybe it's involved with the CRISPR-Cas9, for example, in order to knock down some gene regulation. Yep. For example, as I know, in order to decrease the cell growth, in order to have the higher cell diameter that also related into the antibody production. But for the secondly, because I have not much experience about the new technology for the genetic engineering, but I think mostly they involved with the CRISPR-Cas9 or something else, and also have to take some new technology like flow cytometry or something else in order to select the positive clone.
Now, mostly what we now see, we have expression levels that go from 2 to 5 to, let's say, up to 5 to 10 grams per liter with the transposase technology. And one of the main things is also that we do not use a lot CRISPR-Cas because that is always issues with patent issues and so on. That's very difficult because a lot of things are patented. So it's not easy. You can do it in R&D, but in real production, that's the problem.
Yes, I think so. But in my opinion, we have to figure out first that what kind of gene that we have to do genetic engineering first. And I think not every cell line should have the same gene for the genetic engineering. It's necessary to test for each cell line. So I don't think that we can use the same technology for all of cell line.
Yeah. No, that's true. So that's also mostly different cell, but CHO is, let's say, the main driver on it. I have another question on this chapter 1. That's about, you have in table 4, you give examples of excipients in biopharmaceutical products, and I see in the buffering agents, I see there sodium hydroxide. I know it's a pH modifier, but is it also a buffering agent, sodium hydroxide?
You mean that for the pH modifier?
Yeah, that's by the pH modifier, and then it's a buffering agent. Is it really, is sodium hydroxide a buffering agent?
I think so, because maybe some of a buffering agent also involved with to adjust the pH and maybe have other action also. But sorry, I don't have much information about this.
Mostly the other ones, they have a pK values and so on. And for sodium hydroxide, normally, I think it's a pH modifier, but it's mostly for changing the pH condition, but not really a real buffering agent. Then I have another question in chapter 2. That's page 43. There you see you did, let's say, the UV spectra. And one of the things is... let's say this one is, page 40, figure 1. There you show UV spectra of the different samples, the single clones and from the polyclones. But are these spectra taken during the culturing, or let's say, I know you normally take the harvest then and you remove the cells and then you measure, but are these taken at the end of the culture or also during the culturing, these spectra?
For this one is during the culture because in this research I also monitoring some key parameters such as the cell variability and also the antibody titer. So this spectrum also.
So you did every day, you took a sample and you measure it or something like that during the culturing?
Yeah, sometimes it's some experiment is every day, but some experiment is one other day.
Yeah. Okay. And you had also in this chapter 2, page 43, there you have in figure 2, there you have the percentage of variance explained as a function of the number of the factors used in the PLS models. But what is the first factor? Because you give the different factors and you see that the first factor had the biggest influence.
Yes, for this figure, this show that how much of each factor that can explain the variance of the sample. So in this figure, the factor 1 also can explain the variance of the sample for 45.
Which parameters are in this factor? Because you see that the first one has already the largest influence, so then you know already. Then you can get a good correlation. But do you know in this factor what kinds of parameters are in it?
Do you mean the variance explain, right?
Yeah.
It means that if you get the high of percent variance explain, it's possible that you can use this factor for the calibration model.
Yeah,
but
that's I know.
Anyway, we have also to determine the error of predictive also. So sometimes the factor 1 cannot give a satisfactory of the error of prediction. That's why I use other factor in order to get the good predictive model.
Yeah, but still, it's difficult to see which kind of parameters, let's say, are in this factor included.
Yes, but I think normally the percent variance explained it should have at least like 80 or 85% higher in order to cover all of variance that we can find in the real sample in the future.
Yeah, I know this program Unscramble also, and there you can really main to the main factors what you look at, and that gives a certain percentage that the PC1, the PC2, and so on, that sort of thing. So, but okay, I see that in page 47, figure 5, you have the same again also. I have another question that's about. That's in chapter 4. There you did a lot of, let's have a look, page 990, I think was it. Yeah, chapter 4, you look to the effect of the adenosine and cordicipin on the production of the, let's say, of the different cell lines. Did you also measure in between sometimes the amino acid concentrations or not? Because you see some effects, but self-viability and so on. But did you do some work on measuring amino acid content? Because sometimes it could be that some of the important amino acids that you get, let's say, you have not enough available, so that can have an influence on the culture.
You mean the content of the protein?
Yeah, some important amino acids. Glutamine is an important one. Let's say, did you measure them during the fermentation?
This one for the protein concentration, I use ELISA, sandwich ELISA.
Yeah, that's true. But only the amino acids.
Yes, and this one I have test this ELISA method already that there are the good correlation between the concentration of antibody and the absorbance of the reaction in the cell plate.
Yeah, that's also for the concentration, but I think for the real, the different amino acids itself, I think you did not measure them.
No.
Okay, because it's important to know whether you do not get a lack in the amount of amino acids, because they have an effect on the fermentation.
I think we need to stop this discussion in view of the time. And I would like to thank you for your participation here in this ceremony.
Thank you.
And the discussion will be continued by the second opponent. It's Dr. Sabrina Oliveira from the Division Pharmaceutics, as well as the Division Cell Biology of our faculty here in Utrecht.
Yes, thank you, Chairman. Dear candidate, I would also like to congratulate you with a very interesting thesis, as well as your supervisors. I read it with great pleasure. I think the work is indeed very relevant topic in view of so many biologicals being produced and the wish to have them affordable as well. So first question I have is from the introduction. Maybe you could elaborate a little bit more to explain what you mean with the sentence you wrote, which I will read. So it's where you compare small molecule drugs and biologicals. So you wrote, these products are often composed of monoclonal antibodies, vaccines, blah, 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 and are engineered to interact with specific molecular targets, enabling a level of precision not commonly achieved by traditional pharmaceutical products. So my question is, what do you mean exactly by this level of precision? Is this mechanistically on how the drug works, biological versus conventional small drugs? Or do you have another intention with this choice of words?
Circulator opponent, can you tell me the page number that you refer?
Page 2, actually. Where is it? Yeah, so 6th line on the top.
Do you mean the sentence that about a level of precision,
Yes.
right? Okay, because for the small molecule drug, mostly they act as by binding a receptor, and mostly maybe this receptor have are in various of body. So sometimes the small drug maybe can act like systematic. But for the vaccine or the biological drug, mostly they involve with the immune response, and we can decide that this biological drug maybe act only at the specific CD or the position of gene. That's why I think for the biological drug maybe have more precise medicine than the small molecule drug.
Okay, now that adds on, thank you for the clarification. Although antibodies are also known to have side effects, right? So ideally this will depend on the target that they will bind, whether they recruit only immune cells or they interfere with another target, and where is it produced. So if we would now add to this discussion the tyrosine kinase inhibitors, those are also very small molecules that interfere with signaling pathways. Would you then also consider this precise? Okay, just thank you. That answers my questions. So now I move to page 41. So there you are comparing this methodology that you are introducing, and I will again indicate a sentence just after reference 24, where you say the ELISA method that was used as the reference method could only detect properly folded antibodies, and therefore an HPLC method might probably provide a more reliable estimate for the concentration of antibody. And my question here is, isn't the functionality of the antibody produced also relevant? So can you do without ELISA totally in the procedure? That's the question.
Yes, I think so that for ELISA method, we need a proper of the folded of the antibody, because in this study I use the sandwich ELISA. That's why we need a proper of the 4 molecule. But yes, sometimes ELISA can also use for the functional activity testing also. But in this study, I didn't use the specific antigen. So this ELISA method can only detect the antibody molecule with the a proper folded molecule. But when we compare with the HPLC method, this is possible to determine all of the concentration of the antibody molecule, but sometimes even the proper of the folded molecule or like a secondary or tertiary structure maybe have missing. Maybe HPLC can detect this antibody concentration also, because mostly they related to the mass of the antibody in order to separate from interference.
Mm-hmm. But will that then give you a proper assessment of your sample? Because in the end you want to have a well-produced antibody that is functional in the clinic. Or will that introduce a margin of error?
Yes, because I agree with you that mostly we need the method that have to determine the antibody with the functional. But I think in the screening step, we have only to check first that this antibody production can have the higher production yield or not. That's why at this study, I use just only the ELISA method to check the concentration.
Okay, that's clear. Thank you. So I now move to chapter 3, where you use the Alamar assay. So when I used this assay in the past, I recall that the outcome would vary depending on the incubation time, the temperature, the conditions, the setting. So did you encounter this, and does that bring some challenges in the methodology that you now are introducing, or not at all? So that's good.
I think the Alamar Bool is quite interesting because we can observe the live cell. When we compare with the cell variety determination by using Clipchamp Bool staining, they just only to detect the dead cell. But sometimes we would like to know how much of live cell in order to monitor, and especially for the selection of high producer cone in cell plate that have a small amount of live cell. I think Alamar Bool have higher advantage for this one. So I think Alamar Bool is quite more attractive than traditional one.
Okay. And the variations will be easy to handle within the...
Yes, because we can only culture to add the Alamar Bool and then culture, and after that we can also remove Alamar Bool later. That will not have adverse effect to the cell.
Okay. Thank you for this clarification. So, as a final question, I think I still have.
If you can make it very short and a short answer.
I will try to make it short. So, your work focuses on CHO cells, but HECs are also very often used as a system to express recombinant proteins, also therapeutic antibodies. Was there a particular reason for choosing CHOs here? Yes or no? It's very short.
For my reason, because because my second promoter have this CHO cell, and I think the CHO cell is the most popular for the antibody production in the industry scale, because you can culture it in the high cell density, and because the CHO cell have the similar of glycosylation pattern with the human, and mostly I think CHO cell have a high adaptive to large of bioreactor. That's why I think it's easier than to use HEC cell.
Okay. Thank you very much. I give the word back to you.
Thank you, Dr. Oliveira. And the discussion will be continued by Dr. Marieke Klein of the University of Delft. Please.
Thank you, Mr. Chairman. Dear candidate, first of all, I would like to express my appreciation to join your committee, as it allowed me to familiarize myself with your work. And as was said before, it's very relevant. You capture many different parts of antibody production, cell line selection, actual production, but also the formulation part. And I think we can all agree that this all needs improvement to make these therapeutics more affordable and therefore accessible. And because of the relevance of your work, I would like to dive in a little bit deeper. And I wanted to start with chapter 2 and 3, and if time permits, maybe also a little bit about chapter 4 and 5. Your first two chapters are about the implementation of chemometrics for data analysis. And it's often stated, not only by you, but also in the field, that this will bring us benefits. In my view, we are actually replacing operators and technicians with more highly skilled mathematicians and statisticians. And I was wondering what your view is on the added benefit of these more complex models to look at the processes or cell line selection.
Circulator opponent. For the chemometric that I use, I think this is maybe more benefit. Maybe this is benefit to monitoring key parameter like cell variability or an antibody production. But I know that for the bioreactor also have like a probe that maybe can monitor this parameter also. But as I have some experience with this probe, I found a lot of problem because it also need to validate this probe with its cell line also, and it's quite difficult to validate, especially if we don't have the cell with the under the culture condition similar to the bioreactor. Sometimes it cannot to get the real of live cell. But for the multivariate data analysis, when you get the spectroscopic data, you can create a model for each parameter that you want to determine.
And where do you then think lies the benefit? Is it replacing people or is it something else? I
think maybe it can replace in some lab, because the commercial probe in the bioreactor is quite expensive, and I think not all of lab can afford for it.
Yeah, indeed, making things more affordable, but then we're implementing very expensive equipment is very difficult to balance, I would say. Okay. I would like to start with a question about chapter 2. as far as I understand, your goal is to identify good producers. And for this, you have selected a quantitative regression model. So that means that you quantitate how much is being produced, while the goal is to find good producers. So why did you choose a regression model instead of a classification model where you can just say good or bad, yes or no, which makes the problem statement much simpler and maybe also the modeling much simpler? Could you elaborate a bit on why you chose a quantitative model?
I also have tried to use the classification model, but for my opinion, I think the classification you can only know that this is high, middle, or low producer, but sometimes we need to know in deeper information like about the live cell and also antibody concentration. So I think if we can have a quantitative model, maybe it's better because you can know that how much of the cell or how much of each clone that can produce in order. But when we compare with the classification, you can only say that, okay, this group is high and this group is middle, but you didn't know how much or the maximum of the antibody concentration that you can get it.
Yes, indeed, because good or bad is very relative. Or yes, indeed, I agree with that. Then I wanted to look a bit more closely to the models that you developed, and I think we already touched upon one of the figures. I think it's on page 96. Just double check. Oh no, this is. Sorry, 47. We already looked at this with one of the other opponents, where we see the different latent variables and then the expressed variance, and you made a selection based on that. And I picked up on one of your answers where you said that not only the variance that is explained is important, but also the predictability of the model. So why did you choose to display the variance and not the prediction performance as a function of the latent variables?
Because this one can also show that the optimal factor, how much of the variance explained for that one. And yes, in this study, I also have to show the performance of predictability of the optimal model also. But yes, I didn't show a full table in detail of that.
Could you elaborate a little bit on what you saw when you looked at the prediction of the models for the different latent variables?
Yes, this one is also for the calibration model, and then I also look into the predictive ability in test set validation also.
Yeah. And what do you see when you start adding latent variables with respect to the predictability?
Yes, if you use a higher latent factor, you can get higher, the better of result. But after the optimal latent factor, the error also increase also. That and sometimes also have a 2/5 of the correlation that maybe is not good when you deal with the real sample in the future.
Yeah, so that means that if you increase the latent variables, you introduce overfitting.
Yes.
Model, right? Yeah, and that's why it's more common to see the error of prediction as a function of the latent variables, because if you only show the variance, adding more latent variables will always increase the variance explained, because that is what the mathematics do. With that in mind, I also did not see the root mean square error of your cross-validations. What did you see when you compared the root mean square error of your cross-validation with the root mean square error of your prediction?
Yes, I also look into that one, both of the cross validation and also the external validation.
What did you see?
For the cross validation, when I increase the number of latent factor, is also mostly decreased. But for the external validation by using the test set, after the optimal latent factor, the error of, root mean square of error of prediction increased. That's why we cannot use the high end of latent factor.
So how did you choose the optimal latent variables? Did you compare it to the root mean square error of cross-validation or solely based on the prediction error?
Mostly I use the test set validation because this is can be a represent of us the real sample in the future, and I also look into the bias also.
Yeah, I think combining the root mean square of the validation set will also help you determine the overfitting part. So that might be good. I also wanted to talk a little bit about the UV spectra that you show, and that is page 40, figure 1, and then compared to the regression coefficients.
Can you condense your question?
Yes. So I wanted to ask, where do you see the most valuable information in the UV spectrum?
For the UV spectrum, I use the PCA model first, and then I use the Kennard-Stone algorithm to select which sample will be the calibration and which one is the test set. After that, I use the PLS model, and then because I use like a full wavelength, so we have a lot of variables that can affect to the model. I also have tried with to cut some wavelength out, but it's not. I cannot get a better model.
Okay, thank you for that.
Thank you for coming here and to contribute to this ceremony. Thank you. The discussion will be continued by Dr. René van Ostrom of the Division of Pharmaceutics.
Thank you. First of all, I would like to congratulate you with this very nice thesis. I know it was not an easy road, so please take my congratulations. My first question is about the Alamo Blue assay, which was already mentioned a few times here. Normally, this reagents are based on the conversion of Alamo Blue to the fluorescent rizoruffin. But you use UV-Vis spectroscopy to measure it. Why did you use UV-Vis spectroscopy, and maybe you can explain what are the disadvantages and advantages of fluorescence versus UV-Vis?
Circulator opponent. In this study, I use Alamo Blue as the reference method in order to determine the live cell. But for the model, I use UV spectrum because I think that almost of the lab have the UV spectrum, UV spectroscopy, and because this stage is for the high to selection the high producer cone that I did the experiment in the 96 well page. So I have a limited volume of the sample. That's why I use the nanodrops UV spectroscopy. But the advantage of the UV spectroscopy, yes, because all of the lab have it and it's easy to use, and also we can have a plenty of variable of absorbance in each wavelength in order to include into the model. But for the disadvantage of UV spectro, this is because of there is less specificity because any compound that have chromophore can interfere the UV spectrum. Yes, I know for this, but I think if we can apply the multivariate data analysis, we can remove some noise from this interference.
Okay. What would then be maybe the advantage of using fluorescence?
For fluorescent, yes, for fluorescent have higher specificity, but when you measure fluorescent intensity, you have to know first that what is the appropriate of the excitation and emission wavelength also. And I think it's quite difficult to determine the appropriate wavelength because this sample is quite very complex. So I think maybe yes, maybe this compound have excitation in different wavelength.
Okay, that's clear. I think maybe the sensitivity is better, but I agree with you that it very much is dependent on the environment and other components that are present. My next question is about, I would like to go over to page 70. There you show, there you mentioned in your text, a little below the middle of page 70, that you had a good, figure 5a, you had a good correlation between the predicted values and the actual values, resulting in a Pearson R-square value of 0.84. But I would not consider 0.84 as a good correlation. But maybe when I look at the actual figure 5, I also see the reason why, because there are quite some clones that did not produce any antibody. So, and then what you actually did was you made a selection where you discard the non-producing clones. So actually do